Now, let's investigate the quantum of the decay of the vector W boson minus. And first we'll look at the electric charge. And on the scalar boson minus, the two components, the anti-V prime and the anti-T prime, contribute a minus 2/3 and a minus 1/3, which sum together a minus 1 electric charge. And on the V and anti-V pair, they contribute no charge. So the charge on the composing rishons of the vector W boson minus is minus 1, as indicated by the standard model. Now, if we look at the decay, and we'll see that we have the anti-neutrino and the electron after the components of the scalar boson minus interact with the muon and anti-muon pair. And so we have on the anti-muon, of course, we have a 1/3 and a 1/3 on the rishons, and then on the anti-V prime, we have a minus 2/3, which gives us for the anti-neutrino an electric charge of 0. And on the electron, we have a minus 1/3 and a minus 1/3, and on the anti-T prime, we also have a minus 1/3, giving a total charge of minus 1 on the electron. And these are the charges consistent with the standard model. And of course, on the vector boson 0, the charge is 0. So now let's take a look at the spin quantum. And so, of course, on the scalar boson minus, we have a spin of plus 1/2 and minus 1/2 on the components, giving us 0. And on the vector boson 0, we have minus 1/2 on the V rishon, and on the anti-V rishon, we have also a minus 1/2, giving us a minus 1 spin. And so the total spin on the vector W boson minus is then minus 1. Now, if we look at the antineutrino, which is actually composed of the antineutrino and the vector boson 0 together, on the antineutrino itself, the generic, we have a minus 1/2 and plus 1/2 on the T rishons, and on the anti-V prime, we have a plus 1/2, giving us a plus 1/2. But on the vector boson 0, we have minus 1/2 and minus 1/2, so that minus 1 sum to the plus 1/2 gives us a minus 1/2 for the composition of the antineutrino. And for the electron, we have plus 1/2 and a minus 1/2 for the anti-T rishons, and then on the anti-T prime we have a minus 1/2. So on the electron we also have a minus 1 spin. Now let's see if we get consistent weak charges as they are related in the standard model to the spin. And so the weak charges on the initial vector W boson minus, we have on the vector boson 0 total weak charge, as we saw before, of plus 1/2. And on the scalar boson minus, we have minus 1, so the total weak charge on the W boson minus will be minus 1/2. And of course, if we multiply that by 2, we'll get minus 1 for the hypercharge, which was consistent with the standard model. Now, if we look at the antineutrino, and so we have in the right-hand spin portion of the antineutrino, we should have a minus 1/2. And we see we have a minus 1/6 plus 2/6 will give us 1/6, and 1/6 plus minus 4/6 will give us minus 3/6, which is minus 1/2. But the minus 1/2 will be then summed with the plus 1/2 of vector boson, so we get 0 for the left-handed antineutrino, which is consistent with what is predicted by the standard model. While on the left-handed electron, we get 1/6, and we get minus 2/6, which gives us a minus 1/6 plus minus 2/6, which gives us minus 3/6, which gives us a minus 1/2 weak charge on the left-handed electron, which is also the correct weak charge that is indicated by the standard model. As previously shown, the color charges are consistent with the standard model. Summing to 0 for all compositions. Summing to 0 for all compositions, as the color charge should be for leptons and bosons. And so there we have the decay of the vector W boson minus particle, and we see that not only are the decay products consistent with the standard model, but so are the primary quanta, also all consistent with the standard model.